Hey everyone, this is the last dip that we're going to have into logistic growth. This time we are going to look at the integration of the logistic growth differential equation. So there's a lot to do. We're going to go ahead and get started on our next screen. This time we're going to pick on the Ravenclaw House. Here is some facts, and then we're going to say that Ravenclaw had an outbreak of a different disease called scrofungulus. So here is a number of infected Ravenclaw. Notice how much there are more Ravenclaws that were in the Ravenclaw. I think they're in a tower. And we're going to start with the differential equation for logistic growth. We're going to next separate variables. So we're going to multiply both sides by dt, divide both sides by p m minus p, and that gets us to this equation over here. dp over p m minus p equals k dt. Okay, we're going to now just take a look at the integration of just this part right here. What is the integration of this? Because this is the more intense of the two. So that is all of this over here. Now, 1 over p m minus p, we can break that up into partial fractions. And if you do the partial fraction work, you get that a and b are the same thing. They're both equal to 1 over m. In class, we would probably go over actually show all of those details. But right now, we're just going to say you can try it out if you like. Both a and b are going to be 1 over m. So we're going to take those 1 over m's and we're going to put them on the outside of the antiderivative. So you can imagine over here, our a and our b are both 1 over m now. And so we're going to take that 1 over m and we're going to put it on the outside of the antiderivative because it is constant. And we have the integral of dp over p equals 1 over m integral of dp over m minus p. Now we're in terms of p, so when we take the antiderivative of dp over p is natural log of p. Now we don't need the absolute value because p is a population and populations are always positive. So p is always greater than 0. Now over here, we're going to have to use a u substitution. So if u is equal to m minus p, du is going to be equal to negative dp. So that's where this negative comes from when we take our antiderivative. So we have negative natural log of m minus p. And if we simplify that all out, we're going to take the 1 over m, factor it out of both of these, and we get natural log of p minus the natural log of m minus p. And we're going to put it on pause here for 1 second. Taking a look at the right side, we have k dt, and that's this integral right here, k dt. That's pretty easy. That's just kt plus c. So when you put those two left and right sides together, okay, you get the right side's kt plus c. The left side is 1 over m multiplied by the quantity of natural log p minus natural log of m minus p. Now we're going to multiply both sides by negative m. Okay, now the negative part is kind of the key to make this all actually bearable. So it is kind of a genius thing to do. So when you multiply by negative m, you're going to take that negative, well, the m's are going to cancel out. That's not a big deal. Cancel, cancel. But this negative is going to distribute into the two terms of the left side of the equal sign. So we're going to get positive natural log of m minus p and negative natural log of p, which is what you see here. Positive natural log of m minus p, negative natural log of p. Now on the right side, you just distribute kt times m, negative m, is negative mkt. C times m is just a constant, so we'll just make that a constant anyways. On the left side, we're going to use the properties of logs, and we're going to say that this is equal to the natural log of m minus p over p. The right side stays the same. And now we exponentiate. So e to the natural log of m minus p over p, that's just equal to m minus p over p, which is what we have here. When we exponentiate the right side, that's not really a big deal. But we do have this plus c here. So e to the negative mkt plus c, that's going to be equal to e to the negative mkt multiplied by e to the c power. And this is just going to be a. So that's where this a comes from. So that's a e to the negative mkt. Notice on the left side, we can simplify this to m over p minus 1. So we add 1 to both sides, and m over p is equal to 1 plus a e to the negative mkt. Now we take the reciprocal of the left and the right, and we get p over m equals 1 over 1 plus a e to the negative mkt. Finally, we multiply both sides by m, and we get this beast of an equation. That's pretty amazing. That was like every integration technique we've ever learned we had to use here. Okay, maybe not everything, but most of the things we've learned. Most notably, we needed to use a partial fraction decomposition. So this is a general solution for a logistic growth equation. Which brings us to the box of knowledge. Now, just like in a exponential growth, we don't ever want to integrate this over and over again. It doesn't get any easier. And it's a well-known equation. So if you just memorize the differential equation and the general solution, which is what most people are going to do, then you don't have to do any of the integration here. Now, all of the same properties hold. As t approaches infinity, p approaches m. This is a new one. The limit as t approaches infinity of dp dt is equal to 0. And that kind of makes sense because dp dt, well, the population started to reach that asymptote. So dp dt was approaching 0. dp is a maximum when p is 1/2 m. We knew that. And this is actually a common misconception. So many students forget about this. A is not the initial population. This is not exponential growth. A is related to the initial population, but it is not the initial population. So keep that in mind. Common misconception. Whew. Now, let's get back to Scrophungulus and the Ravenclaws. We know that the Ravenclaw had 50 students in the outbreak, so m equals 50. Okay. P prime is greatest when p is 1/2 2, or p is 1/2 of m. And that happens right about t equals 5. We've got a population, the number of infected Ravenclaw is 27. So let's estimate p prime of 5. So p prime of 5 is about equal to, and I'm going to use a difference here, 33 minus 18 over 6 minus 4. So that's that's just the secant line slope here. We're using 6 and 4 because those are kind of sandwiching that 5. So 33 minus 18 over 6 minus 4. Okay, so P prime of 5 is about equal to 7.5, estimated. Okay, we have values of P5, we have values of P prime 5, and we have M. So now we can use our differential equation to solve for K. Let's go ahead and do that. We know Kp M minus P, that's equal to dP dt. When t equals 5, we've got K. We know P is 27. That's from here. We know that M is 50. 50 minus 27 is 23. And then that's equal to dP dt. And dP dt is, they gave it to me, right? Oh, it's about 7.5. So using all of that, we can just go ahead and solve for K now. So T equals 5, P equals 27. So let's solve. 0.012. Now, just like with the exponential growth equations, we're going to hold on to as many digits of K as we can, because just a little bit off on K is going to make a big difference in our population equation. Now, we're going to substitute the things we know into our equation for P. So, what is M? M is 50. 1 is 1. I don't have a value for A, so I'm just going to put an A there. And this is going to be e to the negative m, so negative 50 multiplied by k, which is 0.012 multiplied by t. Now, of course, I'm not going to multiply by 0.012. I'm going to use as many digits as I can. So when I multiply that out, I get 0.063t. But remember, just like last time, I'm going to hold on to as many digits there as I can. So it's in my calculator stored. Now, how do I find the value of A? Well, we're going to use P5. Okay. So we're making it fit basically right in the middle of our data. So P5 is equal to 27, and I'm going to need some more room here. That's going to be equal to 50 over 1 plus A e to the negative 0.603 multiplied by 5. And using this, we should be able to figure out our value of A. Actually, let's take it to the solver. So as you can see, I'm putting the general solution to the logistic growth equation into my solver. And I'm just going to start substituting numbers in. So let's see. When t equals 27, we don't have a value of A yet, so I'll just leave that at 3. M was 50. K, I don't have that yet, but I know T is 5. Let's remember my value of K. My value of K was 0.012772947. So that's a ridiculous number of digits to have for K. And now we can solve for A. When you put something to start off with, the seed value for A, make sure you have a positive number. So there's my positive number, and I'm going to go ahead and get my value of A here. Negative 19. Interesting. Oh, duh. I feel so dumb right now. Our numerator is wrong. This is supposed to be m on top. All right, so that should make sense. Let's go back to here. Let's solve. Again, I want you to put a positive number here to start off with, and I'll start with 20. Okay, great. That gives me a value of A, which is 17.443. So let's go ahead and write that down, 17.443. Great. That gives me P equals 50 over 1 plus 17.443 e to the negative 0.603 t. Now, next thing we're supposed to do is graph all of the data together with our equation, and I kind of did that previously, so I'm just going to go ahead and put that in here for you. Here on my calculator, I've put all of the values. L1 over here is going to be is T. L2 over here is P, the number of people infected. And if I, over here, Y1 is going to be equal to 50 over 1 plus 17.443e, blah, blah, blah. I use an X instead of a T, otherwise it's not going to graph. But that is the growth equation, the logistic growth equation that I found using the calculus stuff. So let's just graph everything together. To graph everything here, I'm going to do the scatter plot first, and L1 and L2. And we're just going to zoom statistics. And we'll see how closely we fit here. Now remember that I used rounded values for A and K and M, but that looks pretty darn good. Okay, I think that fits pretty well. Not so good over here, pretty good over here, and shockingly, over here on the tail end of the infection, we got it looking pretty good as well. So let's screenshot this and put this into our calculus trainer. Of course, you're probably supposed to be doing this analytically, but I don't know how you're going to graph this curve without actually putting this into your TI calculator. But let's just say that our exponential curve fit the data pretty nicely. And, this data here, this isn't, okay, it is fake data. I was going to say it's not fake data. But it didn't fit exactly into this curve. I actually did a simulation here to figure out how this would go. And this is what we got. So I think it's a pretty good job. Which brings us to the important ideas of logistic growth. Like with that was barely English, but like with our differential equations for exponential growth, the logistic growth is a well-known differential equation, so there's no need to show integration. This differential equation leads necessarily to this general solution. Okay. Unlike exponential growth, A is not going to be our initial population. And in order to get all of these values correctly, I highly recommend you use the solver function on your calculator. This is why you have it. So, with all of that said, let's check our understanding. In a recent survey, the Ministry of Magic Affairs determined that the number of mice, non-magical mice of course, on the Hogwarts campus to have a logistic growth rate given by dp/dt equals 0.3 p minus 0.0003 p squared, where p is the number of mice and t is in months. At the time of the survey, t equals 0, there were 61 mice at the Hogwarts School for Witchcraft and Wizardry. So, according to this model, how many mice can Hogwarts accommodate? So this is the similar trick to how we did this on our last calculus trainer. We first factor out p, and then we factor out our coefficient of p inside the parentheses. So we're going to factor out 0.0003. So we get dp dt is 0.003p 1000 minus p. Reading that tells me k equals 0.0003 and m equals 1000. We can answer the question to part A. How many mice can Hogwarts accommodate? Hogwarts can accommodate 1000 non-magical mice. Now, without intervention, when does the model predict that the population will reach 700 individuals? So, based on what we're seeing here, we're going to have to go to the population equation. So the population equation, remember, have this memorized. This is m, 1 plus a e to the negative m k t. So let's substitute the things that we know. M is 1000. 1 plus a e to the negative mkt. So negative m times k is 0.3 t. Sorry, 0.3. All right, so we have that. The next thing to do is solve for a. So let's go ahead and get to our solver on our calculator. We'll put in the things that we know. Okay, we still have the growth equation here, so we can just start substituting things here. I'll leave population alone. I know m is 1000. I don't have a value for a. I do have a value for k. K was 0.0003. And now we're going to have to figure out our value of t. So if you remember from the problem that we read, when t equals 0, there are 61 mice. So let's get back to here, and when t equals 0, the population was 61. So I have a value of p, I have a value of m, I don't have a value of a, I have k, and I have t. Now, I generally like to start a somewhere at, half of p. So half of p is what, 30? So we're going to start around 30. Okay, I know it's 30.5, but, somewhere around there. And we'll hit alpha enter to solve, and that should give me my value of a. A is 15.39. So let's take a note of that and write it on our paper. So we got a equals 15.393. And then finally, we'll solve how many mice? Yeah, when will we have 700 mice? So when is the population going to be equal to 700? Let's take a guess here for t, and I'm uncomfortable putting a 0 there. I do want a positive number, so let's put 10. And we'll alpha solve. And the number we get is, I got pretty close, 11.937. Back over here on the paper, we should probably write down the population equation fully expressed. So that is 1,000, 1 plus 15.393 e to the negative 0.03. Can you believe I made the same mistake twice? 0.3 t, and the population equals 700 when t equals, what was that number, 11.937? Let's read again to figure out a unit here. T is in months. So at month 11, so after 11.937 months, the mouse population will be 700. So that's it, everybody. I hope that the calculus didn't seem overwhelming to you. There really isn't a whole lot of calculus to these logistic growth equations. You just have to know how they operate. You need to know how to create one based on the constants, and then you need to know how to solve them or solve for them. So that's it for us. We'll see you next time here at the Ferraria Math class.